Hey guys, what's up? Eddie Alho here with KissAnalog.com. Today we are going to look at how the PWM, the pulse width modulation, works and how it controls or regulates output voltage. Okay, so we're going to use this little board that we've been playing with, and I'm going to come over and show some stuff in the notebook. I'm going to draw some pictures, attempt to, and then we'll show the signals on the scope too. All right, so yeah, let's do this. I think this will kind of help give an idea. What we're going to do is we're going to cover voltage mode control, okay? Then we'll do current mode control next time, so then we can kind of compare them without making this video too long. We'll see how this goes. All right, hey, thanks guys. Let's jump over here and take a look. All right guys, so just to remind you about this boost regulator. This is the input power, these two terminals, and this is the output. The input has a diode on this heatsink and the input capacitor, and then on the output we have the switching transistor on this heatsink with the output capacitor, and these are the output leads. Okay, and what's missing here is the toroid, the inductor I put on this side of the board. And this is the feedback resistor part of it. There's two resistors, a resistor with this pot that sets the output voltage. Then on this side is where all the electronics are, the control chip right here, and the sense resistor down here, current sense. So I soldered the inductor so that I have this loop in series with the inductor leads. That way, because normally the inductor would just solder into, these two pins right here. So these two pins of the inductor would solder right here and here. So instead, one lead soldered there, the other lead soldered to this wire, and then the wire brings it over to the normal resting place. So that way I can loop my current probe in there and monitor the current. So take the trusty old hand tech, clip it on there, and that current induces a field into a magnetic structure that's inside this. So you can't see, it's covered by plastic. Kind of see a little bit of it right there. And so that comes down, and there's like a kind of a core like this inside here. And so this magnetic pickup picks up that field and senses the current. So you can kind of think of it as a transformer. This is one winding and the other winding's on this side, so transformally coupled. Alright, so let's just kind of walk through this setup here. What I'm going to do is take this voltage probe here, set at a ×10 position on this switch here. And I'm going to reach down in here and take this little hook and clip it on to that leg. There's 3 legs on this transistor down there, and that far one over there is the gate. So I'm going to go down there and try to clip it on that. Okay, so now that's clipped on there. I'm going to flip it over because we're going to hook up some things to this side. We're going to hook our current clamp on this guy. Okay, and then I'll set this guy in its times 100 position, I think, because we're going to be reading a little higher current. So I'll put that right there. I'll hook up this ground from this probe over here to our output ground. Now our output ground, this is the input, these 2 pins upside down, and this is our output. But you may notice on the board the copper is connected there. The returns on both these black wires are the same. You can see a little isolation around that positive pad, and you can see that little line right through there. That's where there's no copper. So the positive one here is tied to the output here. Okay. Alright, and these are the connectors from the power supply, so we'll just hook that up. Positive to positive, black to black. Okay, that's going to be our input power. Now, just to let you know, let's zoom out and take a look at this. This positive lead right here, before it goes to the power supply, it's going to go through this multimeter. So it comes out the common here, and the other lead actually goes to the power supply. So this meter here can read how much current is coming through here. So the current comes in here, into A, and out the common lead. We'll just set this meter over here. Alright, and then the output is going to be a pretty simple connection. Alright guys, then the output is a simple connection. We just take our red and black lead from our other multimeter. We just clamp on that guy and then clamp on this guy. Okay, and then we'll take this return probe from our scope. I'm going to pull this out a little bit so I can grab on. Okay, that's from our scope. Okay, and then we'll put that multimeter right here. So that'll be looking at our output voltage right here. And then over here, the meter you can't really see right now, is our input current. Alright guys, and I'm going to take this multimeter right here, and this will read the input voltage right here at the meter, or right here at the board, because the multimeter, that little current loop, it'll drop a little bit of voltage to the current loop in there, and also the test lead. So we're going to measure the voltage right here as it goes into the board. Okay, now these two leads here, this red and green one, are to this active load right here. See at the top of the screen here, right here where I'm pointing. So we'll take, and then that'll give us the voltage right here and the current. So we'll put that there. Red, red, black, black. Now we have our ground from our scope probe, right? So what we're going to do is come over here and just clip it in there. So it's on the jaws. Alright? So we're going to look at the gate voltage. We're going to look at the current going through the power supply. This is a current on the output and the voltage. Alright guys, here's a bird's eye view. You can kind of see a little bit better. Some of the connections are right here we saw hooked up. Now I swapped out that tech meter, just put it in the Astro just to give the Astro a little fun. So it's in the amp setting, DC, and we're in the 10 amp post over here. They have a milliamp, microamp, and a 10 amp. So it's in the 10 amp scale, and the common one is right here that's going to the supply. So there you go. Alright, and then we'll take this voltage probe and we'll go to the switching node. So I'm going to connect that right here. And we'll take the ground over here as well. Okay, and then we'll take this voltage probe and we'll put it on the output. So we'll just come over here and yeah, we'll clip right onto this guy, and we'll put the ground in the same spot. We'll clip it onto this output probe. There we go. Now let's just bring up the input voltage so you can kind of watch it happen. Alright, so what we see is we have 0.98 volts here at the output, 0.82 amps, here's 0.82, so input current, output current match, and the input voltage 1.58, so the output is 0.98. Okay, so we have a little voltage drop on that diode. Okay, you can see I'm up to 6.6 volts input. Right around 10. So if you can see down here we're 7.85 volts, 8.6. There's just a diode drop difference. So 8 volts right now, 8.6. Okay, now right around 10 you're going to see it jump up. This voltage here is going to jump up. Okay, we're 10.3 right there. So it jumped up to 19.3 volts. So it looks like I'll put the input at 12 volts. Make sure it's got enough voltage to run. with no drops across the input. So we have 12 volts here, and we have 20.1 volts down here. Okay, and right now we have 16.48 watts. It's 0.82 amps. And this load, the fan starts spinning to keep it cool. Here, I'll reach over here and turn on the load a little bit. So I'm approaching, okay, I'm going to set 2 amps on the output, and we have 3.9 amps here. And we dropped a little bit below 12. On the output we're 19.9. So I take this up a little bit higher. Let's go to 4 amps. Okay, we're right at almost 4 amps, 3.99. And the input voltage, let's drop a little voltage across the lead, so I'll bring it up. Okay, there's 12 volts there. So the input's 12 volts, 7.2 amps, and the output is 19.7 volts at 3.97. So it's regulating pretty well. That's around 80 watts, 79 watts. So that's not too bad. 79 watts at the output. So I drop it down to about a half an amp, and the input, you know, even the fan stopped running. The load's running pretty cool. The input's 0.85 amps, output's 12.99. That's just a voltage drop across the leads and also across the current sense resistor in the multimeter. So higher current, more drop, DC resistance drop. Alright, so what we want to do is we want to talk about PWM control, pulse width modulation. So this gate right here has a gate drive signal that turns it on and off. Okay, so the gate drive signal, let's say it's a 10 volt signal. So it's going to have this clock signal coming in. And it's going to go up and down, and then sometimes it might get narrow to control the output voltage. Okay, so then it might come back up. So anyway, you're going to have this pulse width modulation. So the width of the pulse is going to modulate, meaning changing the width to control your output voltage. So it's going to have some feedback. It's going to have to look at your output voltage to determine, you know, how wide to make that pulse. Well, now actually this frequency, it's a fixed frequency. Now I may not have made the right scale here to make that a fixed frequency, but it would be a fixed frequency. You'd have these other things like a capacitor you would choose, and that would be your CT for your timing capacitor, and then you'd have a resistor. Depending on the controller chip, they can work differently, but often you'll have something like this. So internally there'll be an oscillator, and it'll apply a current, and depending on the value of that capacitor, it'll have a ramp, and then depending on the RC time constant, it'll just change the ramp charge. You'll set your frequency by that. Okay, so let's just say that what you're getting is this ramp that comes up. Okay, so let's say your ramp is something like this. Comes along, ramps up, and then it discharges. Once it hits this peak voltage, there's an internal circuit that will discharge that capacitor, and then it comes along. Let's say we're going to have a 50% duty cycle here, so it's on half the time, off half the time. It's charging half the time, the other half the time it's off. Okay, so that's your ramp voltage. So your oscillator sets up this ramp. Okay, now what happens is, let's say you want a pulse wide like that, then you're going to have two signals. You're going to have a feedback that's going to compare itself to this ramp voltage. So if your feedback voltage we're going to take this feedback and we're going to have to go through a circuit. I'll show you that in a moment. And you're going to come out with the error voltage. Okay, so let's say voltage error. And let's say that voltage error is down here, along here. So if that's the case, when this guy ramps on, okay, your gate voltage is going to come along and it says, oh, we're turning on. So it turns on, and then it comes along until it sees where this crosses this signal here. And it says, oh, I turn off. Then it comes along. He says, oh, I turn on again. And then he says, oh, I'm turning back off right there. So you end up getting this pulse like this. Pretty narrow pulse. And if your air signal stays the same, then you would keep on getting these pulses like that. So these narrow pulses. Okay, now let's look at the other case where, let's say you come along and we're going to redraw this ramp signal, okay? That's our ramp. Whoops. Shoot, sorry. That's your ramp right there. Okay, sorry about that. And then in this case, let's say the VE is up here. Okay, now you can probably guess what's going to happen. You come along until this crosses right there, and then you drop down. So now you're on for a lot longer time, right? So you come on, and then let's say right there, and you turn off. I'll draw another line right here. So then turn back on, and then come over there and turn off again. So you can see how your pulse width is going to change based on where your error voltage is, okay? And that's how your pulse width modulate, okay? And so this error voltage compares itself to this ramp, and then that's how this control chip knows how long to turn this gate voltage on, by comparing those signals. Alright, so let's see if I can draw this circuit. Let's just say that we're going to draw a circuit that's in between, that kind of takes all this information and, you know, controls this gate drive. So what we're going to do is we're going to draw this chip here, this little function inside this guy. Sorry, you can tell already I'm a bad drawer, but okay, this chip has a SR latch, let's call it. It's a Q, that's just a letter, but that's going to be our gate drive, okay? That's our gate drive output, and these pins here, this is this is kind of a SR latch, okay? So this is a set and a reset. So when you get a signal here, it turns that Q on. And when that signal goes low, it stays on. It just latches it. And then you have to get a high signal here, a high signal here, to reset that back to 0. Okay? Alright, so then on the set signal, we're going to say we're going to have this oscillator right here. It puts out just a signal at the frequency we want, okay? Something like that. It's probably a really narrow pulse. Something, you know, so it's just set at the frequency that is set up by this RC time constant with the current source built into that. And so let's say on the output of this guy, we'll draw that capacitor, the CT. And inside this guy, he'll charge this guy up, so you'll get that ramp. And then at a certain point, it'll have a little FET in there that'll discharge it. So it'll come along like this and have this little ramp and a discharge. So he sets up this ramp right here. Okay, and then we'll have this other comparator circuit here. I'll just try to draw that right here. And he'll come into there and drive this reset pin. So always draw the minus sign on top, plus on the bottom. So on the minus, we'll have the voltage error coming in here, and on the plus, it'll be this ramp voltage. So when it gets high enough, it'll reset that. So it might take, if the if this VE is all the way to the top, it'll have to come all the way up here before it gets higher than the VE signal where it goes positive. But if the VE is very low like this, then it won't take very long before this goes positive. And so that's how, comparing these two signals, it can reset this guy. And every time the oscillator starts to charge this capacitor, it'll set this, and that's what, so every time it does it, it'll set it so the gate will go up, and then it'll wait until this ramp gets above the VE before it gets reset. Okay, so now you're asking, okay, well, but how do we get the VE signal? Well, let's just come out here a little bit farther, and I'll just draw another, attempt to draw another op amp, or so draw a minus here and a plus here. Alright, so we know the feedback's going to come in here, right? Well, the feedback comes into this pin right here, to the minus, and the plus, let's say this is going to be our VREF. Now often in these chips they can be 2.5. The newer chips are a little bit lower because we have output voltages that are lower than 2.5. So that's why I use voltage resistor dividers to divide the voltage to come back to feedback. So let's say if the VREF was 1 volt, then you could control anything from 1 volt and above by, bringing this voltage back. If you had to control, if this VREF is 2.5, like it was commonly done, and you're trying to control 5 volts, you just take 2 resistors, divide that 5 in half, and bring that back here. So now let's just say the voltage is starting off at 0 on the output, so the VREF is going to be higher. So this is a plus, so that drives that minus, so that's low. Alright, so if the output voltage is near 0, then the VREF is going to be high, so you're going to have a plus here, and this VE is going to be high, so it's going to be like this condition. So you get a wide pulse, and then as it charges up the output, the voltage comes up, then eventually the feedback goes high, and then this goes low, and then you're in this condition where the VE is lower. So that's one example of how pulse width modulation control is done in voltage feedback. So this is voltage mode feedback. We'll cover current mode feedback next video. Okay, so just go over the scope setup. Channel 1 is going to the gate of that MOSFET. So that's center screen right here, and it's set for 5 volts per division. Should see, I'm thinking 5 or 10 volts, probably 10 volts, so go up a couple scales. And so channel 2 is the switching node, and that is going to be maybe 15, 20 volts, whatever. And so that's the blue one. So we're set here at 5 volts per, so it's 5, 10, 15, 20. So we should see that. And then channel 3 is the current probe, and set that center of the screen, and it's set for 5 amps per division. So we'll see what we see there, and depending on the load and so on. Okay, then channel 4 is our output voltage. So it's set for 5 volts per, so if we're at 20 volts, it'd be 5, 10, 15, 20, so it should be around here. Okay. Now on trigger, next guy over here, just hit the trigger menu. It's set on, where are we set? Channel 1, source channel 1, so it's on the gate of that FET. That's pretty good signal to be synced up to, I think. Right now it's on high frequency reject. We'll just put on AC, I think. And then slope is rising edge. Level is around 5 volts, 4.56, somewhere in the middle of what I think the gate will be. And automatic. And so let's see where channel 1 is set up. Channel 1, DC coupling, 1 meg, inverts off. We got bandwidth, so we're going to just filter out some of the high frequency noise. This goes up to 20 megahertz and 10x position. So channel 2 should be pretty much the same thing. We got that menu turned on. And channel 3, and it's pretty much the same thing, except for over here we're on current probe and 100x, because we're on the 100x range on that meter. And then channel 4, the last voltage there, that menu's turned on too, 10x, so same as the other voltage channels. Alright, and then as far as our horizontal time base, we are set at 2 microseconds per division, which is probably pretty good. We could go, say, 5 microseconds per division, and if this is switching around 100 kilohertz, we should see 1 full cycle and a couple divisions. So, alright, well, I think we're ready to turn it on and see what happens. Okay, so I'll just turn off that bottom menu. You know what, let's set up our measurements. I just noticed all these measurements are set on RMS right now, and then peak to peak on this one. Let's just go to measurements and remove measurements. Let's remove them all, start over. Let's add some measurements. So on the gate, what we want to do is maybe, let's just look at duty cycle, I think. We could look at frequency, but I think we'll get that anyway with our frequency counter. So let's go down to duty cycle. Let's select that. Okay, channel 2 is our switching node, so let's go to, oops. Hold on a sec. Source is channel 1 on that last one, so let's go remove measurements, remove all, add measurements, source channel 1, duty cycle, yes. Okay, channel 2, so source channel 2. Let's do peak to peak on that. Okay. Channel 3 is current. Let's do peak to peak on that guy. Yeah, let's do that again. Okay. And channel 4 is output voltage. Let's just do max. Let's just do RMS on channel 4, the output. Alright, let's see what we got. Okay, so duty cycle channel 1, peak to peak on the switching node, peak to peak on the current, and RMS on the output voltage. Alright, so let's bring up the voltage. Okay, so we're bringing up the input voltage, and you see the output voltage here in green and the switching node both rising together because it's not switching yet. The voltage is going straight through. We're 8.5 volts, you see right here 9 volts on the output. Okay, there we go. So I'm going to take it up 12 volts. Alright, that's 12 volts input. You see the output's 20 volts. Now all these things on top of each other make it kind of hard to see. Right now I'm going to turn off the current. And I'll turn off the switching node too, so I can take it just to the gate voltage and that. You know what? And I'm going to take the gate and put it down right at the same spot that the output voltage starts from. And that'll be 15 volts. You know, it's 3 divisions down, so it's 15. So there's the gate. It looks like it's good. 20% duty cycle that's on, then it's off 80% of the time. See, it's about 19.5. And you can see the switching node the switching noise when it turns on and turns off. Now look, I'll go to channel 4 and I'll go to full bandwidth. See how the noise just gets a little bit higher? Now if I use good grounding techniques on my scope probes and so on, yeah, I could drop that down. So that's why just letting the scope filter it for me is fine. Just for what we're doing here, that's fine. So there we go, there's the gate. And you know what, I'm going to drop the gate so it only takes 1 division so it doesn't clutter up our other waveforms. So we can look at the gate time when we're turning on and off, and we can watch the duty cycle change. So for instance, I'll drop the input voltage down to 10 volts. Alright, we're right about 10 volts there. And look, the duty cycle went up to 26.5%. So has to get wider to try to keep that voltage up. The output voltage is still 20 volts. Okay, now take the input voltage up to say 15 volts. Okay, there's 15. And look, we're down around 14% duty cycle, and we're actually trying to miss some cycles. If I come over here and change this, the scale, to include more cycles, you'll see how we're kind of missing some. It's kind of skipping sometimes. You see that? Here, I'll freeze it now. See how it's on and off? We don't have much of a load, and the input voltage is high enough that we just don't need to draw that much current. That's what's happening. So if I drop the input voltage back down to 12 volts, see, I'm right about 12 volts right there. Now see, with lower input voltage, it takes more current to get the same power on the output. Remember, switching power supplies are constant power supplies. They'll put out a constant power to maintain their output voltage. Now let's increase the load and see how that changes things. Okay, right now we're at about 0.67 amps. Okay, I just doubled it. I went about 1.5. See the duty cycle, it's up 30%. The output's still regulating at 20. Okay, I'll take the current up to say 4 amps. Alright, now look at that duty cycle. It's almost 50%, it's 47%. That's a pulse width modulation chip adjusting the pulse width modulation. See, pulse width modulation, so it changes the width of the pulse to modulate, you know, to keep that output constant. See, if we go down real low current, we'll start skipping pulses. Like there's no current, so it skips a bunch of pulses because we just don't need to charge the output to keep the voltage up. And then with load it increases. So that's what I want to demonstrate. The more power you need on the output, the more on time the transistor has to be on to charge that inductor a little bit more to switch that output voltage. The inductor has to charge a little higher, get more energy per pulse so it can keep that output voltage up. Alright, so now let's go ahead and turn on the current so you can just actually see the current. Get rid of the menus. Now that current's kind of dirty, but you can see how when it's on it rises, and then there's a switching noise when it turns off. Then it discharges, and then it charges back up. So you can see the switching noise when it turns on, and then the switching noise when it turns off. Okay, now let's turn on the switching node. Alright, so I'm going to turn off the current just so it'll be easier to see what's going on here. Just get rid of some of the stuff. Okay, so what we're seeing here is when the gate turns on, that switching node gets pulled down because that FET is essentially shorting that switching node to ground, pulling current, charging up that inductor, and then it lets go. And when it lets go, so look at that noise spike. It lets go and there's big noise spike, then it flattens off, and then the output kind of runs out of energy. So that inductor gets charged up, then jumps up, then discharges, and then it kind of starting to run out of juice and starts to resonate, and then gets pulled on and goes to that cycle again. Now if we need even more load on the output, see how the resonant part kind of goes away? The inductor's filling up with current, and it pretty much needs a whole cycle to transfer energy. Alright, and notice the duty cycle, how wide it's getting. Okay, so we're right there. We have about, let's see, I'm going to bring the input voltage up to 12 volts. I'll bring the current, okay, right there where we kind of fill up. We're about 3 amps output. It's about 61 watts. So yeah, we're about 61 watts. So let's look at the current. Turn back on. So you can see the current's 5 amps per scale. So it's going up almost 10 amp peak, and then it discharges. So that's how the duty cycle, how the pulse width modulation controls or regulates the output. Alright guys, what do you think? Did that make sense? We're going to cover this more. We're kind of taking bite-sized chunks to kind of ease our way into this stuff. But I hope that helped, and we will cover more of this control theory. And I'll get into some formulas and some of that kind of stuff so we can start kind of seeing how to design this thing, okay? So for right now I was just trying to cover kind of a higher level, and then we can soak down into the meat of the thing, okay? So hey, hope this is helping. Give me your ideas, what you'd like to see. But yeah, we've got several videos to go to fully cover this boost regulator, okay? And then it won't really be fully covered. I mean, we'll always come back with more details, more elements that we can go deeper into. All kinds of different control techniques, for instance. But yeah, I hope this one helped. Alright, hey, thumbs up guys. Thanks for watching. We'll see you next time.